All right, y'all. So this is going to be the third video in our bonding series. So last time we talked about and concentrated on ionic and covalent bonding, and we looked at how you draw Lewis structures for those, and we talked about the intermolecular forces that occur between covalent molecules. There is a third type of bonding that we need to address. So with ionic bonding, that was a metal and a non-metal combining. With covalent bonding, it was two non-metals combining. The third type is when you just have metal atoms combining, and which is called metallic bonding. Metallic bonding is unique in that with ionic we had one atom giving, one atom gaining. In covalent we had sharing. With metallic bonding you have what's called the electron C theory, where all of the atoms in the metal are going to dissociate their electrons. So all of the electrons dissociate away from the nuclei and become like this floating cloud or sea of electrons with the positive metal nuclei embedded throughout. And the fact that these electrons are not attached to any one atom is why metals have their characteristic properties. So metals are malleable and ductile because if I apply pressure to, or apply a force to these atoms, these electrons are going to work like grease and allow these nuclei to just slide around and assume a new shape. Versus if I tried that with ionic or covalent bonding, then they would just shatter. They would break because their bonding is much more rigid. The positive and negative charges in here are all attracting to each other, which means you have to overcome all of that attractive force in order to get a metal to phase shift, which is why metals have the highest melting points of anything on the table, and trying to get them to go to gas phase is nearly impossible for most of them, mercury being a notable exception. Then in terms of luster, if I hit this with any kind of energy, like light, then these electrons are just going to bounce it back, and that's why the metals are shiny. And then in terms of thermal and electrical conductivity, well, with electrical conductivity, just like with the ionic compounds, electricity can just bounce along these electrons real simple. It just goes straight through. And then with heat is another form of energy, and again, that can be transferred really easily across the cloud. So everything that a metal can do is because it has this electron sea of electrons. And then these are just some definitions of everything. So malleability means it can be hammered or shaped, and ductility means it can be drawn into a wire. Luster means it's shiny. And then the high melting point means that those delocalized electrons are attracted strongly to all the nuclei, so it takes a lot of energy to get it to melt. And then with the thermal electrical conductivity, that's just exciting the electrons, and they can flow freely and transfer that heat and electricity. All right, the other thing we're going to go ahead and talk about in this video is what's called VSEPR theory. And so we're kind of going back to covalent bonding for a minute. VSEPR theory stands for valence shell electron pair repulsion theory. And what that says is that in a covalent molecule, the electrons in the bonds and the lone pairs on the middle atom in the molecule are going to arrange in such a way that they are not pushing away from each other as strongly. So remember, electrons are all negatively charged, and like charges repel each other. So if the molecule doesn't arrange itself in a certain shape, then those repulsions will be strong enough to break the molecule apart. So you have this definite shape that you can predict of an molecule based on what it's bonded to and how many lone pairs you have on that center atom. And so this is a general formulas for all of the electron geometries that you're going to need to know. So if what I have in the molecule is just 2 atoms or 1 center atom and 2 atoms attached to it, and there are no lone pairs on that middle atom. So we're only caring about what's on the middle atom here. We call that shape linear because the 2 bonded atoms are going to orient themselves so they are 180 degrees apart and have this very straight line shape. And molecules that take this shape may or may not be polar depending on what's being bonded. So if it's just 2 atoms together and one is more electronegative than the other, you will have a polar molecule. If it's 3 atoms like this, most of the time not. If we have a molecule that has a center atom, 2 bonded atoms, and 1 or 2 lone pairs on the middle atom, we call that shape bent. So bent molecules, literally the bonded pairs are pushed down, and the lone pairs are sitting up high on the middle atom. So we get this bond angle of around 104.5 degrees. And anything that has this shape will always be polar because the lone pairs on this middle atom create a large space of negative charge on the middle atom. And then the 2 bent down atoms usually become your positive region. If what we have is a center atom and 3 attached atoms and no lone pairs, then that is a trigonal planar molecule. And the angles between the bonds that are on the center atom are all 120 degrees. So it's 3 sides of a triangle. And again, because this is symmetrical and the electronegativity differences are all going to be the same between the center atom and the lone atoms or the attached atoms, this will not be a polar molecule. If we have 4 atoms on the center atom and no lone pairs, we call that tetrahedral. And the bond angles are 109.5 degrees because you have 3 of the bonded atoms forming like the base of a pyramid, and then the 4th bonded atom is going to stick up into another plane. So like these 3 would be in the X plane and this would be the Y plane, so that they're now oriented geometrically as far apart as possible. And again, this would not be polar because it's symmetrical and all of the electronegativity differences are similar. And then if we have 3 bonded atoms and 1 lone pair on the center atom, we call that trigonal pyramidal. So if you compare these 2, it's just like we took this top bond and replaced it with a lone pair. And so the lone pair actually does distort these bond angles slightly so that they're somewhat less than 109.5. And this will also be a polar molecule because those lone pairs are going to create a very negatively charged region on the molecule. We can also have some advanced shapes. I'm not going to make you memorize these or anything or know about them, but I just want you to mention them. It goes on the idea that any element in the 3rd period and above can actually violate octet rule because it can hide extra lone pair of bonds in their d orbitals. And so we can see things like trigonal bipyramidal, seesaw, T-shaped. There's another way to get to linear, but you have like 3 electron pairs and 2 bonded atoms on a center molecule. And then octahedral. So just it's good to know that, you know, we do have some molecules that will take some weird shapes, but they can do that because of those d orbitals that we talked about when we talked about electron configuration. And then we can go on. There's also square pyramidal and square planar. But again, we will not be looking into these very hard. So you mostly are needing to know about the shapes that were on the first table. So you need to know about linear and bent and trigonal planar, trigonal pyramidal, and tetrahedral.